Hey, I'm Michael Sigmund, and this is Lab 4, Circuits and Capacitors for Professor Berger's Physics 2212 class. The purpose of this lab is to comprehend the effects of resistors in series and parallel, and to understand how to use multimeters to measure potential differences and conventional currents, and use CCK to modern behavior of capacitors and ohmic resistors. The physics principles we will use for this lab is Ohm's law, which is that voltage equals current times resistance. Capacitance, which is capacitance equals charge divided by voltage. The node rule, which is the currents flowing in equals the currents flowing out. And the loop rule, which is the total potential differences around entire circuit equals 0. So, the procedure for this lab is to first download the circuit construction kit, and then to build a following circuit with two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters. So using Ohm's law, we can predict the current, which we can divide the 3 volts by the 147 ohms to get 0.0204 amps. And so the actual current is 0.02 amps, so it's a little bit precise than the predicted current. And then to find the reverse current, we just make it negative. So you should then replace the second ammeter with a voltmeter. The estimated readings are 3 volts, 3 volts potential at battery, 0 volt potential at resistor, and an open circuit. And the actual reading is 3 volts, and the voltmeter has infinite resistance because it is open circuit, which leads to no current flowing to the voltmeter. So for this, we are showing the potential differences around the circuit. On the right, you can see a picture of the circuit and the different points. On the left, you can see the values for each one of those points. And for the to find the change in the potential difference in the round trips, you just add up all the values together, which you get 0 volts, which supports the loop rule. And in the bottom right, it shows the amount of resistance at each one of the points. So for this, we are putting the ammeters in parallel to a 100 ohm resistor, and the current increases from 0.02 amps to 0.06 amps due to the parallel ammeter. Less current encounters the 100 ohm resistor, and this is supported by Ohm's law since the resistance decreases, the current increases. For this, we will apply Ohm's law to find the current of the ohms of each of the components. For the resistor with a value of 47, it comes out to 48 ohms. For the resistor of 100, it comes out to 102 ohms. And each of the other two values for the wire and the ammeter is 0 ohms. And so the calculated resistance is higher than expected due to the lack of precision in the ammeter. The second part of this lab requires you to construct this circuit. You use a 9 volt battery, 200 millifarad capacitor, a 10 ohm bulb, and a 20 ohm bulb. For the charging part of the capacitor, it starts at the maximum current and decreases exponentially. And when the capacitor is fully charged, there is no current. The charging time for a 10 ohm bulb was 10.2 seconds, and the charging time for the 20 ohm bulb was 19.5 seconds, which makes sense considering that it would have double the resistance for the 20 ohm bulb. And for discharging, the maximum current, the current is maximum at first and decreases exponentially with time, similar to the same with the last one. And when the capacitor is fully discharged, there's no current, and the discharging times are for the 10 ohm bulb is 14.1 seconds, and for the 20 ohm bulb it's 27.4 seconds. So to determine the time constant, we can use the equation on the top left, and we can ln it to solve for RC. So the slope is y equals negative 0.1424 x plus 0.049, and we get that from the data that we inputted in the graph. So we can have the negative reciprocal, put the negative reciprocal of the slope equal to the RC, and we get the RC equals 7.04 seconds. And finally, our what if questions. So the first one is, what if we were doing this lab in real life and used an actual ammeter instead of an idea simulated ammeter? What's the difference about a real ammeter, and how would it affect the currents you hooked it up to? So a real ammeter has resistance, and real life readings would be less accurate. And what if we're doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor reach full charge? The capacitor would be charged instantly. However, in real life, all components have resistance, so it would require time to charge the capacitor.